So yeah, welcome to this session on geometric deep learning, and really I'm going to cover the key ideas and not delve too much into the math, although I will get into some math which I think is cool, but for instance I won't say too much about representation theory, both because we've covered that already and because I know that's one thing that sort of scares people about GDL, so I'll mostly focus on also the stuff that I also find more intuitive, namely the geometry and analysis part and signal processing. But yeah, keep in mind that I'm only going to give like a bird's eye view of like, okay, how do you go about making equivariant model for something, for some kind of domain, but like I won't give specifics for any of what I'm be talking about. So, but also feel free to interrupt me at any time to ask questions, because also it should probably be a bit shorter than the usual sessions. Also, sorry for being late again. So let's start with just like a simple outline. So I'll briefly like talk about Euclidean spaces, which are like the default domain for neural networks, and what's so good about them, like what is so great about data that is defined on the Euclidean space, and what we can do with that. And then unfortunately not all data can live in a Euclidean space, or at least there are some kind of data sets or data objects that don't really live in a Euclidean space, and getting them to like representing them in a Euclidean space can be tricky and maybe does not capture all the information that we care about. And then I'll go over the CNNs, which are like maybe the starting point of GDL, which is, okay, let's look at CNNs and like generalize them for these other kinds of data that we have. And then I'll go about the broad ideas of how to go about this. As a caveat, note that I'm very much biased here in that I'll cover stuff that I think is more interesting, and there'll be a lot of hand waving and personal intuition. So again, feel free to interrupt me if anything is not clear. So also, why do we need this, right? Why do we need to do GDL, right? Can't we just make a massive neural network and just take the bitter pill? Well, one is that sometimes we have some weird data, like some kind of graph or some kind of point cloud, or like an object is not just one point but a bunch of data points, or maybe we have a model that should be able to take in sets as inputs, and it has to be like because you can't really represent a set in a computer, right? You have a sequence of objects in a computer, and so if you want to represent a set, there are multiple ways to represent that set, but if you want your model to not care about that, you need to make sure of it. And also, it's also the case that we have not a lot of this kind of data. So like maybe you're a chemist or a biologist, and okay, your data set is like maybe a couple thousand, a couple hundreds of molecules. It's usually not enough data to apply the standard techniques. So you need some kind of more data efficient architecture. So that's another thing that we can do with these kind of models. And also, maybe you don't have that much compute, so you can't just you can't just make GPUs go burr, or maybe you don't have any other GPUs, whatever. And the third one, but this one's biased, is the math is pretty cool. That's maybe not a need. Whoop, someone left. Okay, we'll see if they come back. So Euclidean spaces, they're pretty great. There are a few reasons for that. One is that they have, and here mostly stating the mathematical structure, is that okay, first of all, they're vector spaces. So not only do we have a norm, so we have a metric space, and because we have a metric space, we have topology. Similarly, we have distance between points, so again the same 2 points. We can even explicitly compute shortest paths between 2 points, right, by simply doing a linear interpolation. Actually, that norm, at least on Euclidean space, it also comes from an inner product, so it's an inner product space, which gives us some kind of geometry because we can take the angle, right? If you have to take the inner product between two vectors, and you take something like the sine of it, or the cosine, you get the cosine distance, and that sort of measure the angle between two vectors. And so we also have angles as a thing we can measure, because vector spaces sort of are built upon the real numbers. We also have all the properties that we inherit from the real number. So, okay, real numbers have an order relation. It's usually not so important, but sometimes it's useful. There's a lot of algebraic structure, right? We have a field R with the plus and product operation and some neutral elements. There's a differential structure, right? We can do calculus on the real and Euclidean spaces. We can also measure things, right? We can take a region of a Euclidean space and compute its volume. We can take the integral of some function on some domain. Okay, sometimes the integral goes to infinity, but usually we can take some kind of measures. So it's also another thing we can take measures of. And so all of these are like to show that Euclidean space have a ton of mathematical structure, and it's sort of why they're the default setting for machine learning, because they're both well understood. They have all these nice properties that make a lot of things easy. Sometimes you have nice algorithms and so on. And also they're just easy to represent in a computer. You just get an array of numbers, of floating point numbers, and that's essentially a vector. Unfortunately, not all things are vector spaces. For instance, well, we can have graphs. So a graph is simply a set of vertices and edges in different fields. Sometimes they're also called nodes and links or nodes and relations, whatever. But yeah, the idea is that you have a bunch of points, and then you have connection between those points, and they're supposed to be meaningful. An example of this in like empirical context would be social networks, right? Maybe you're looking at you're working for Facebook or Meta, and okay, you have some connection, the friendship between people, and maybe you want to infer something about it. Maybe if this person likes Coca-Cola, then his friends might also like Coca-Cola, and so you send the ads to them. Another one is chemical molecules, right? You have atoms connected with chemical bonds between them, and then form some kind of structure. And one of them is simply you can view it as a graph, and there are a few models in like chemistry applications that use this graph representation of molecules. In biology, you have something called gene interaction networks, that because genetics is a very complex thing, but you can sort of study like pairwise interaction between different genes and how they interact with each other. Another one is sort of customer product network. So for example, like Netflix had this big data set of customers and movies they had watched, and you want to sort of extract data about like user preferences to maybe recommend movies or series to people. I also mentioned sets. Sets are sort of like graphs without any structure. And yeah, so I think I've already explained why you might have sets as our data set. Another one is differential manifolds, and they sort of come into multiple flavors. So, okay, we covered last week the basics of differential manifolds, and okay, in practice you don't get like a pure differential manifold as is. Like it's a continuous object, you can't really represent it in a computer, but you can get some kind of 3D scan data, like maybe you have a LiDAR from a driverless car, or maybe you have an MRI scan and you're trying to find tumors. And okay, you have data that's essentially representing some kind of space, and you have objects in those, like the tumor might be some kind of ball or something, and you're trying to look at it as a shape. And so if it's a shape, you can approximate it by its surface, and that surface you'll usually describe it by some kind of manifold. And there are multiple ways to like represent a manifold in discrete terms, usually with a 3D mesh or some kind of point cloud or various other things. And in this context, we really care about having a sort of description of this shape or geometrical objects to study it, to say, okay, maybe this is like a bad tumor, or this is a benign tumor, or whatever. Okay, so all of these objects are not vector spaces, but you can always get like a free vector space on them by using this one simple trick, is that if you have any set X, then the set of functions, or maybe some subset of functions from that set X to the real numbers, or really to any algebraic field, this forms automatically a vector space. So that's pretty nice. You get your domain that might be like very non-Euclidean, but you can always obtain some kind of vector space of signals or functions defined on them. So for example, if you have a graph, well, you can take like functions on the vertices, and that gives you a vector space. You can take a function defined on the edges, that gives you another vector space, and immediately you have a vector space of signals on the graph, and you can find some relation between, okay, these signals on the graph and maybe some properties of the graph. Note that okay, in practice you may have a graph with different kinds of data, right? Maybe you have, like, the nodes are individuals, but then you get data about their age, their gender, their like how much time they spend on average on off topic or whatever. And same with interactions, like maybe you interact with a different choice with different people, or maybe like this might be okay, this person does not like this person. So there might be any kind of signals and of various dimensions. And for manifolds, or discrete representation of manifold, there are a bunch of things, but the sort of two most common and easy to wrap your head around is first a scalar field, so basically a function on the manifold that returns some kind of scalar, so maybe like the heat, or I don't know, the density of rabbits. So this would be a scalar field, so a function from my manifold to the real numbers. And the other big one is vector fields, where instead, remember again, right, a manifold, there's this local tangent space that tells you, okay, if I move in this direction and there, and so you can sort of build a function that gives a tangent vector to every point of your manifold, and then you can try and follow this vector field and maybe end up somewhere different. And so in general, yeah, you can, there's a whole lot more example of these, but those are like the canonical examples. One note is that, so I mentioned that, okay, you can approximate your continuous manifold with a discrete representation. And the key idea about this is that if you squint hard enough, like, everything is a graph. And so, for example, if you have this like continuous donut or torus, you can discretize it by representing it as a graph. And so you sort of like drop vertices on it and then connect it with links. And the key thing about this is that, okay, this is a discretization of my continuous object. I can take arbitrarily fine discretization, right? I could add more, I could just have a fine grid, and so the intuition is that this is a better approximation of the continuous object. And you can actually formalize this in saying that, okay, some kind of object defined on this discretized object sort of converge to the continuous version. In particular, if you have, we'll see later that you can sort of define a differential operator on the graph, and if you use the right kind of differential operator, it will converge in some sense to the corresponding differential operator on the manifold. A side note is that, okay, I showed graphs, but you can, if you wanted to have like faces and volumes for your discretization, you can totally do that, and it's something called simplicial complexes. it's a whole theory, and it's been gaining traction in network science and also a bit into machine learning. And yeah, so there's also a lot of beautiful mathematics there. So now let's talk about convolutional networks. And so if we go back like to the basics of like how does a CNN work, right? You have at the input some kind of image, like maybe it's something from MNIST, and okay, it has a width and a height because it's a discrete object. And then usually we separate it into various channels, like maybe red, green, blue, and maybe you add more channels later. And we do a linear operation of convolution. So like a convolution is a special operation, but it's also linear. And the idea, right, is that you have you take a patch and you apply some kernel, and that gives you the value of this pixel over here. And you repeat this as you slide this sort of filter over the entire channel. Then, because this is still a neural network, you apply nonlinearity pointwise. That doesn't change. And then usually we also pool, like we condense these channels into smaller images. So we coarsen the thing, and that's usually both to save on memory and maybe to sort of handle different scales on the image. And so there are like three important things here. One is that images really, they're just signals on a grid. So we can, yeah, just think of this as a grid. Note that a grid, you can think of it as a graph, right? You could imagine a graph right, this would be a simple grid. You can think of the grid as a graph. So grids are special kinds of, or special case of graphs. And you could also think about it as a discretization of like maybe a function defined on the unit square, or some kind of square, or yeah, some kind of square that is continuous. The other thing is that, okay, we had this convolution that is a linear transformation. That it's nice because it has weight sharing, so it's in some way parameter efficient. And importantly, it is translation invariant, because we have images and we want to, that if we shift this 2 a little bit, our model should still recognize it as a 2, so it should be invariant to some kind of translation and more generally some kind of symmetries. Maybe if we rotate the 2, we also want that to be recognized as a 2, and so on. And then there's this final thing of pooling or coarsening that lets us sort of handle multiple scales, right? Maybe here this filter just looks at 3 blocks of 3 pixels, and when coarsening, we're effectively looking at sort of larger areas in the image. So keep these in mind, because they'll end up being the key ingredients in the equivalent architectures. But first, I will dive a bit deeper on convolutions, because there's a ton of interesting mathematics also related to representation theory, but I won't go too deep into that one. But the idea, right, if you have some kind of function here on the entire real line, and maybe you have 2 functions, we can define their convolution product as simply the integral of from -infinity to +infinity of x of v times theta u minus v, the dv. And a nice and sort of well-known property about that is that if we take the Fourier transform of x and theta, Fourier transform being defined as this one, there's a really nice property that the Fourier transform of the convolution x and theta is simply the pointwise product of the Fourier transforms of x and theta. But it's nice, so because instead of computing this ugly integral, you now have to compute 2 maybe simpler integrals, or maybe use FFT to make that your life simpler. Note that we could also look at the discrete version, like maybe instead of continuous function, we have like discretize or samples of our functions at regular points. And we can still do some kind of Fourier or convolution and Fourier decomposition. So the convolution just looks a bit like this. I'm abusing notation a little bit, but we can also do some discrete Fourier transform. And again, it satisfies this nice convolution property. That's the Fourier transform of the convolution is simply the pointwise product of the Fourier transforms. Okay, so that's nice, but there are a bunch of other things. One nice thing is that the Fourier basis is an orthogonal basis of the space of signals from Z1 to R. And same thing, if you have like this discretization, it gives you an orthogonal basis of this vector space. So usually when you have a vector space and you get an orthogonal basis, you're pretty happy because like it's the best kind of basis you can have. And it's also a basis that sometimes you can interpret it a little bit, or it gives you some kind of description of your signal at different scales. So if you look, for example, at the various Fourier functions, as the wave number or the frequency increases, then you get these higher and higher frequency terms. So the first one is just a flat line, so that might be like the base level of your function. Then you get this very low frequency sine wave, and then as you go on, you have more and more detail. This is nice and important because it means that if you want to add some kind of regularization, right? Maybe you want your signal to be not super high frequency. Maybe you say, okay, past some frequency it's just noise. Then you can just get rid of all these high frequencies and get a smooth signal. So you can think of this as some kind of regularization. The Fourier basis is also important because it's connected to the so-called Laplacian operator. So on the real numbers, the Laplacian operator is simply the second derivative. And I think on Rn is so it's like this would be on R2, it would be this one. So usually it's like the sum of the second derivatives for along each coordinate. And why this? So what's the connection between the Laplacian and the Fourier functions? It depends on your domain, right? Because you can always, maybe instead of R, you could have some different domains. But the key idea is that first of all, this is a differential operator, so it's actually a linear operator on the space of functions, and it actually has eigenfunctions, so the same as eigenvalues, eigenvectors, but in function spaces. And in fact, so in general, if you take like this exponential e to the I omega x, you take the second derivative and you get essentially minus omega squared e to the I omega x. But this is a complex valued function, so if you take its components, you see that the sinus of 2k pi x, note that here I'm writing 2k pi because it's usually the case that we restrict the domain to 0 pi or 0 1. So we need continuous functions on 0 1. And then so the Laplacian applied to sinus of 2k pi x is minus 4k squared pi squared sinus of 2k pi x. So sinus of 2k pi x is a eigenfunction. It satisfies the eigenvalue equation for the operator, and it's the same thing for the cosinus of 2k pi x. And in fact, that's just the Fourier basis. So what we see is that the Fourier basis is a basis of eigenvectors or eigenfunctions for this Laplacian operator. So okay, that's one connection, and it's connected to another really nice and important property, namely the heat equation, which is one of my favorite differential equations. It's simply you take du of dt, the time derivative, is simply minus some d, which is just a diffusion rate, times the Laplacian of u, and you take some initial condition, And what this does is that it sort of smooths out the initial condition mu0 as t goes to infinity. So again, it goes back to this idea of regularization. You sort of take your signal and you get rid of the higher frequencies first, and you get something that's a little bit smoother. Now, another key thing, well, it's not key, it's more of a nice trivia, but it should give you a bit of intuition why this whole Laplacian operator is pretty important. Is that if you take what's called the fundamental solution of the heat equation around some point, so the fundamental solution is the solution where the initial condition is like a Dirac delta at some point x prime. So initially all your mass is like at single point, and then you look at what the solution looks in the as t is positive. Note that strictly speaking you need some more heavy duty mathematics to define what it means to have a solution in this case, but let's not worry about that too much. But let's just say that the solution, it's also known as the heat kernel. It's some expression of t and y, so for any point, and it's not x prime but just x here. It's 1 over this square root times e to the minus x minus y squared over 4 dt, and so this should remind you of the the Gaussian distribution, and indeed it is. So it's more for intuition, but you can see that it's sort of related to the Gaussian distribution. And remember, the Gaussian distribution comes up everywhere in mathematics and statistics, so this should tell you that there's something going on here. Okay, so I'll finish up with the Fourier basis and move on to the more interesting stuff. So yeah, the recap is that the Fourier basis is nice because it satisfies the convolution theorem, right? So convolutions are easy. It's an eigenbasis of the Laplacian, and the Laplacian has deep connections to geometry and also regularization. So generally the Laplacian or Laplacian types of objects will be sort of our gateway to defining these other architectures. It's also, that's more of the representation theory, but I said we wouldn't go too deep into it, but like the Fourier basis are the irreducible representation of the circle group, and also it can be discretized, and we have efficient algorithm to compute the Fourier transform, namely the FFT. Now the question is, can we get the same for other domains? The answer is yes, at least for the first three. We usually don't get efficient algorithms. Like you just have a linear problem to solve, and it's not as fast as the FFT, unfortunately. But the other parts, the mathematics, is still nice and true. So for example, for a graph, we can define something called a graph Laplacian, and the way you do that is simply you take your graph and you construct its adjacency matrix. That's so it's just a matrix that indicates you like it has a 1 if there's an edge between I and j, and 0 everywhere else. Note that implicitly this definition you need an order of your vertices, right? You need vertices labeled 1 to n. And so there's a bit of a caveat here, is that in principle you could order your vertices arbitrarily. So there's not just one adjacency matrix, there's many of them, but it's just a thing to keep in mind. And then we have sort of multiple Laplacians, but the two most common are the first one on the top, the so-called combinatorial Laplacian, and simply for that you take minus a and you add a diagonal matrix D, and it's a diagonal matrix where the elements dii is simply the sum. So it's the sum of along j of aij, and so it's the degree, or you can figure out the degree, so the number of neighbors of node I in the graph. So this is a standard object in graph theory, but usually we prefer the second one to call strictly speaking, it's the random walk Laplacian, but there's another version called the normalized Laplacian, and simply you take the normal Laplacian, divide it on the left by the degree matrix, note that this requires that there are no nodes of degree 0, but usually that's the case in most interesting applications. And the second matrix is usually a lot nicer for a bunch of different reasons, specifically regarding like its spectrum has nicer properties. But regardless, we have some notion of Laplacian, and note that okay, it might seem weird, like this does not look like the Laplacian as the differential operator that we know. But if you think back to like the grid example, right? I mentioned that a grid is a graph, and if you construct a Laplacian, it looks like what you'd get if you did a finite element discretization of the Laplacian on your grid. So it sort of fits as the Laplacian has this sort of idea of it's a discretized version of this differential operator on some kind of space, but for arbitrary things like graphs. Then for manifolds, we have this thing called the Laplace-Beltrami operator, and it's defined as the trace. So for our function f, it's defined as the trace of the Hessian of f. Note that the trace and Hessian here. Okay, I saw your comment. I'll go back there. So the trace and Hessian are defined up to this metric term. So, okay, so what did you exactly not understand here? The part about the graph Laplacian, or? Okay, so you don't see how the like graph Laplacian corresponds to the like the differential operator. Because in that case, I can. Okay, I'll assume that's what you meant unless you correct me. But like, let's say we just take a simple graph, path graph. Right, this is our path graph. Okay, it's labeled 1, 3, 4, 5. Then we can construct the adjacency matrix. So the adjacency matrix would be so 5 zeros because the adjacency matrix, and then just ones on the other diagonals. And then the standard Laplacian. So the degree here, right? The degree here is 1, 2, 2, 2, 1. So the graph Laplacian would be 1, 2, 2, 2, 1, and then just minus 1. I think that's. The void in the matrix obviously should be 0 elements. Now, if you think of like this, let's take 0 to 1 and then take some function on it. Right, let's call this f, and maybe I want to approximate the derivative of f using a finite element approximation. So to do that, sort of partition my I discretize the unit interval, and then I get this different points. So maybe this would be f0, f1, f2, etc. And then the finite difference approximation for a derivative, it would be f of I. One way you could compute it is simply taking f of I plus 1 minus f of I. Let's say I have like h between any 2 points. Right, this would be like a discrete approximation of the derivative, and then you can do the second order one, and usually if I did this right, I think you can do f prime of I plus 1 minus fi prime, and this I think you end up with so expand this, you get fi plus 1 minus 2fi. Ooh, maybe that's okay. No, I think to get that you need to use forward and backwards, but normally one of the things you can get is minus fi plus 2fi, something like this, over h squared. So okay, I'm sort of going a bit fast, but good. Compute this as either this one or f of I minus 1. I think if you combine these two, you can get this expression on the bottom. If you look right, you get minus fi plus 1 plus 2fi. Yeah, so I'm just doing a finite different approximation of f prime prime. But if you look at this Laplacian over here, right, I have minus 1, 2, 1. And so if you have like a signal defined on your graph, like this graph, you think of it as like a discretization of the unit interval or some line, and then the Laplacian looks like these coefficients on the bottom for the finite difference approximation. So that's what I meant when I said that the graph Laplacian sort of corresponds to the finite approximation discretization of the standard Laplacian. Up to this like h factor, but yeah, so yeah, that's the thing is that so what do you mean if I pick a different graph? Like if I change the order of the vertices, or if I have a different graph that does not look like this? Like if it's the second case, then yeah, obviously if I have this graph here, like a cycle graph, it's a different thing. And if I get just an arbitrary graph, it will be it obviously won't correspond to the finite discretization, but you can sort of keep the intuition of, okay, the graph Laplacian is the discretization of the Laplacian for some kind of space, but that space might not be a line or something really recognizable. Sometimes it's not even a manifold. Anyway, I think we can maybe come back to this later, but just keep this intuition that the graph Laplacian really sort of works like a differential operator on graph signals. And if you do happen to have a discretization of a line of a manifold, it sort of matches what you'd expect. So maybe I think I forgot to say that usually this the reason we prefer this random walk Laplacian is that in some algorithms like the diffusion maps, this matrix or this operator in some sense converges to the Laplace-Beltrami operator. So if your graph is like a discretization of a manifold, then the random walk Laplacian will converge in some specific sense to the Laplace-Beltrami operator on the manifold. But obviously you could have like graphs that don't correspond to any manifold, and so the interpretation, how to interpret that is less clear. Okay. Okay, but yeah, I think we can go back to this at the end if you want. So, okay, I spent a whole lot of time talking about analysis, signal processing, and Fourier basis and convolutions, but there's also the symmetry part in that, okay, the standard convolutions, they are translation invariant, but in general we want some kind of equivariance or invariance with respect to some kind of group of symmetries. That's one thing that, okay, if you have an object that has symmetries, right, maybe you can reflect it on along some axis or do some kind of operation and it's the same. That's a symmetry, and usually symmetries form a group. Or maybe not even usually, I think pretty much always. And so we have these two definitions of a function, a signal on some domain, and it's defined to be G invariant for some group G if, so again, I'm sort of relying on some of the stuff we saw for when we talked about group presentations at the beginning of the reading group. F applied to rho of G, where rho of G is just some group representation of a group element, little g, applied to X, this should be the same as f of X. So it's invariance to whatever group action. For example, if I have some kind of model that should handle set as input, I want the output of my model to not depend on the order. So if I have any permutation here, it shouldn't change anything. And if you prefer looking at commutative diagrams, they're on the right. And then similarly, function is G equivariant if f commutes with the group representation. And so an example of this would be, maybe you have a model that computes some kind of latent in an image, and maybe you want that, okay, if my image is translated, then the latent should be translated in exactly the same way, maybe. Okay, so let's look at a few examples of symmetries for these non-Euclidean domains. So I mentioned already sets, and that sets, their natural symmetries would be permutations, or really the symmetries of the way we represent these sets in a computer. And the reason we care about that is that really the elements of a set have no special order by default. And so usually the function, a function that's defined that takes sets as input, should not depend on the order of these elements. For graphs, it's a similar story, it's also permutations, because I mentioned right that the adjacency matrix is up to the ordering of the vertices, and so the ordering, right, it's a permutation. And so again, it's sometimes useful to say that I want my function to not depend on the order in which I label my vertices to construct the adjacency matrix. And strictly speaking, but I don't think it's discussed much in the GDL literature. But there's also another kind of symmetries of graphs called an automorphism group. Like very briefly, a graph automorphism is like a permutation of the vertices that leaves the adjacency the same. So for example, like if this is my graph, I can sort of swap these two vertices out of order, I still get the same adjacency matrix to that. And these automorphism groups so these permutations that don't change the adjacency matrix, they form a group, and it usually has some nice connections and properties related to the Laplacian, but it's maybe less known. Okay, so that's graph. So discrete objects. For manifolds, okay, I don't have like a nice concrete example, but because manifolds have these metric structure and these nice rigid properties, a natural notion of symmetries is what's called an isometry, right? Maybe I have a sphere and then I rotate on the sphere by some angle. That's still a sphere and that hasn't changed anything, so it's an example of an isometry. Another thing is gauge symmetry. So yeah, gauges are a bit more advanced, but if you remember this idea of the tangent space, right, that at every point of the manifold we had this local vector spaces, then gauge symmetry is a sort of a generalization of that, where you have to each point of your manifold you have a vector space, but it's not necessarily the tangent vector spaces, and then you have these symmetry operations and symmetries between these attached vector spaces. And both of these are sort of natural notions of symmetries for manifolds, and usually come with some kind of Lie group structure. So a Lie group is just a group and some kind of derivative or calculus structure. Very roughly. So we talked about images already, right? We have translations. Sometimes we also want rotations or maybe scale. So different kinds of operations. And then another example that maybe not often thought, but the GLL people will often tell you that, okay, if you have a transformer model for sequences, it's also a special kind of geometric model, specifically because you act on sequences, and really a transformer or attention, it works on a complete graph if you squint hard enough. Then okay, it should be the same as a graph, that it should be invariant to permutations, with a caveat that obviously when you add the positional encoding, you sort of break that permutation invariance, right? Because you actually do care about the fact that your input comes in a certain order and not a different one. Okay, I'm getting to my last slide. Again, no like actual detail on how to build these today, but we can see about that later. The sort of general recipe for constructing a equivariant architecture, or maybe invariant if you prefer. Let's say we have a domain omega, and then maybe some subdomain omega prime, or like maybe you could think of omega prime as like a condensed or compressed version of omega. Maybe it's like a coarser digitization. So those would be domains. And we have a symmetry group over omega. Maybe it's all the symmetries, maybe some of the symmetries, or maybe it's some kind of very weird thing. We can always construct a G equivariant function f from the space of signals on the domain, and then this attached little c is sort of the kind of signals you have, maybe different channels, and to some set or space y. And the form of this function is something like this. So at the input on the right we have a B, which is a linear equivariant layer. So for example, for a graph you'd use some kind of something based on the adjacency matrix or the Laplacian. So that's the equivalent of the convolution. Then you apply the nonlinearity, that's the same as always. Then a pooling, so again, same thing as the pooling operation or coarsening operation in the CNN. So that's your basic layer, and then you stack those as deep as you want. And just at the end, optionally, you can have like a global pooling that is G invariant, and it just directly maps to Y. And so with this is sort of like a general abstraction over what CNNs do. I know it's very, very abstract, so if you want more, let's discuss it. can I touch a bit on the case of continuous groups and using the regular representation like in LeConv? Okay, this is where I must confess I'm not super familiar with this. So yeah, I'm very much risking talking nonsense here, but ooh. So I guess maybe one usual problem with continuous groups is that you cannot, in most cases, you cannot represent them like exactly. You always have some form of discretization or some kind of truncation, so it's one reason, and sometimes it's also more complicated. I think, for example, there are a few works where you do look at Lie groups on manifolds, and then you have to use the like exponential map and logarithmic map. So I guess tentatively, but I may very well be talking out of my ass here, is that it's probably not more popular because one, it's more math, it's more complicated, and it's also probably doesn't play as well with GPUs as just the standard vector space. But I really don't know enough about this particular literature. So I think I didn't respond to your question in DM. Yeah, definitely. Yeah, basically what you just described is stuff. I think, like, I can kind of speak from experience about sort of continuous stuff. Is that I once tried to, I guess these things called neural operators. I think Hawk knows about them, where you, in the abstract, it's like this model that directly handles functions defined in function spaces and does some kernel operations to them. And so you have like these integrals to compute. Obviously, you cannot exactly compute an integral and exactly represent any function in your computer. You need to represent it in a finite way. So usually you pick a basis of functions and you truncate it and represent it. The problem is that it's usually very expensive, and you have these either QMC or some kinds of numerical integration. It's very expensive, and so like when I try to do that for a bit of an evil project, one problem that has that okay, if I try, I want to compute the my integral, but it doesn't work on the GPU, so I have to like do some kind of Fourier method or whatever. So I think probably a big obstacle is just the fact that you cannot train these kinds of continuous models easy on the GPU, because finding like numerical quadrature solvers that work on GPU is very hard. I think I know of one, and I don't know of any code for it. But yeah, definitely underexplored, but probably for good reasons. Okay. Do we have any other questions? Maybe Hawk, if you want to ask more about the like graph Laplacian stuff, or something else, maybe, I don't know. So I think in the case of Lie groups you have a bit more structure to work with, and even the methods that exist today work with the tangent space. You are always doing something in the Euclidean space. Correct. But then, unironically, I think a big obstacle is getting these things to work on a GPU. Because if you want to do something at scale, and you can't do it on the GPU, I think like immediately you lose maybe 3/4 of the room. But yeah, probably Lie groups. If you have like suggestions of stuff we could read about these models on Lie group, it would be nice to cover them. I think one consistency is mostly memory related, since for a regular representation you can have a multiplicative factor in the number of channels. Yeah, absolutely correct. Probably memory problems don't help either. But otherwise you should be able to do everything else on the GPU, sampling, yeah. Yeah, well, it's always a question, okay, can you do on the GPU, and then is there software to do that easily? But I think, yeah, back to the like example of neural operators. Okay, the abstract thing is we have this function space and we compute these integrals, but in practice, use the Fourier neural operators would just cheat and discretize it using the Fourier transform, and then it's just back to matrices again. Yeah, matrix exponential available on GPU, not sure about the log. Yeah, I guess in principle it could be done, but probably not enough people know or care about it. Anyway, I think, Hawk, I saw you were typing. Do you have... Yeah, please go ahead, and then we can end. Oh, no, they joined and left. Okay, I'll pass on like asking questions for now. So I guess thank you both for sticking out to the end. So as always, because I was very high level here, also a bit because I didn't have too much time to prepare the slides, I'm very sorry. But yeah, is there like anything more precise you would cover? I think we discussed a bit about like Lie groups and stuff. Like maybe, yeah, is there like any specific topic in GDL that you'd like to cover next? And this time it would be more in depth about the models and stuff. I guess maybe I can just put up a poll for that on the thread. Okay, I see no silent responses, so yeah, I'll ask on the thread, and oh, one person is typing. Yeah, of course, the regroup stuff. So yeah, I think I'll put it up to a vote in the thread, and we'll discuss it more. But yeah, if you do have like some papers you can read about the Lie group, I think you showed one. You sent one in the thread at some point, but maybe we show it. Yeah, so thank you both for coming and sticking out to the end. I hope you enjoyed it, or at least it was interesting. But yeah, if you want to dig more, don't hesitate. So yeah, with that, I think we'll leave it for today. So bye.